Hello everybody and welcome to another video in the OpenFoam guide course. In today's video, we will continue exploring meshing and take a deeper dive into blockMesh. We will do this by walking through a fluid flow example, where you will learn how to think about the domain of your project and how to move step by step from a simple schematic drawing to an actual computational mesh. For this purpose, I have chosen Poiseuille flow. It's a classic example and it's easy to understand and visualize the flow pattern. And you can easily validate the results you get from OpenFoam against the analytical solution that is available for this problem. So if you remember from previous videos, we said one of the first things you do in the CFD analysis is to identify the fluid domain and the geometry if you have internal boundaries. And here you see the domain of the problem is just a fluid flow between two plates. Then you identify the physics involved. Here we see a fluid flow moving from left to right under the pressure gradient. In the left we have a high pressure, in the right we have a lower pressure. And we assume that the flow is steady, incompressible, and 2D laminar flow. Then we identify the boundary conditions. For the problem here we have an inlet fluid flow velocity, outlet atmospheric pressure, and fixed walls at the top and bottom, where the fluid flow velocity is 0. There is something you need to know about your domain here. If you want to simulate the flow after being developed, fully developed, you must have a domain size that is larger than the entrance length. As you see from this schematic, if your domain is not long enough, you want to reach a hydrodynamically fully developed flow. Okay, as the flow is symmetrical, we can get a benefit from this actually to decrease the computational time by solving just half of the domain as you see here. So instead of solving the whole domain, I solve for the lower part only. And this is how the blockMesh code sees your domain. As you see, I added just one cell in the Z direction as OpenFoam deals with only 3D mesh. Then I choose the 0 point to be my origin. So this point in Cartesian coordinate will be 0x, 0y, and 0z. Second vertex, I move in the x direction, say 30 mm to 0.1. So this vertex will be 30 in the x direction and 0y, 0z. I just want to let you know that the order in which you write the vertices doesn't matter. However, the index number of the vertices will be assigned based on the order you write them, and these numbers won't match the ones shown in the schematic here. So be careful with defining the block and the boundary faces. It's better to draw your schematic and number it in the way you like it. Okay, let's continue. Moving from 1 to vertex 2, which has a distance in the x direction and y direction. It will be 30 mm in x, 1 mm in y, and 0 z direction. And from 0 to vertex 3, we just move 1 mm in the y direction. For the front face, it will be the same, but we add a distance in the z direction, as you see here. Okay, now we have a solid understanding of our problem. So now we move to OpenFoam and see how we can implement this. First of all, we find a suitable solver to solve our problem. Going to solvers, our case is incompressible, and it's a steady state. So a steady state solver or unsteady solver can solve it, and it should give you the same results. So you can try, for example, IcoFoam, which is a transient laminar solver, or SimpleFoam, which is a steady state solver. I will use SimpleFoam. You can visit the source code if you need to know more about any solver by opening solver.c file. Okay, going to run directory where we build the case directory of our problem. Here you can write and build the input files for the case from scratch, create the case directory, and then create the main subdirectories 0, constant, and system. Then the input files in each directory. But this is so hard, at least for me. So what I'm doing is finding a tutorial case that is close to my desired simulation. Then I modify the input files to match my model. For this, let's visit the tutorial directory, going into SimpleFoam. I know this one here, and I know it's close to our problem. So I copy it. Now we start modifying these files to match our case. Starting with the meshing, we modify blockMeshDict. I delete these vertices, and I don't want these variables. I just need one block, so I delete the rest. Here you see the boundaries, almost like in our case. We just redefine the faces. So start by writing the vertices. Let me open the schematic drawing again to just make it easy. Vertex 0. And you can write a comment here if you want for yourself. Let me write the rest. Then write the block vertices. The number of cells in each direction. Gradient. For this flow, it's better to increase the mesh density near to the wall. So say this number, or 4 is good. I keep the edges straight line as it is. Move on to the boundaries. Inlet is the one in the left here. To define the face vertices, start from any point, then use your right hand, the thumb pointing outward, normal to the face, and the rest of the fingers rotate in the direction you follow to write the rest of the vertices. Okay. The outlet is the one in the right here. For upper wall, the symmetry plane here, you had the freedom to change these names here to make it more descriptive for your problem, if you want, but I keep it here. We need to change this type from wall to be symmetry plane. These two here are good. I keep them. Lower wall is this one here. Its type is wall. Then writing the front and the back. I think we have done here. Actually, we don't need to write a semicolon here. I delete them, it's okay. And don't forget to check the scale. By luck, this scale fits our case, so I keep it. So now we run blockMesh to see. Oops. I have a problem with the boundary face definition. We can check this again. The vertices are correct, I think. The block is correct. So let's open the schematic again to see the boundaries. The inlet is good. The error was in this batch. So where is the problem? Oh, here. I wrote 02, it should be 12. Okay. This is good. Now we have the computational mesh. It's good to know how to read the output of the commands in Linux, especially if the software doesn't have a GUI like OpenFoam, because that is the only way to know what is going on in your process. For example, we have seen an error message before, and now we see the mesh information, number of points, number of cells, and yes, we expect this number, as we set 120 cells in X direction, 20 in Y, and 1 cell in Z direction. Let's calculate this. And here you see. I like doing these calculations. Again, number of faces, number of internal faces, and if you subtract number of internal faces from the number of faces, should give you the number of boundary faces. Let's verify this. For instance, say number of boundary faces equal to number of faces minus number of internal faces. And then compare it to the summation of these faces here. Yes, equality is true. And if you want more statistics about your mesh, you can run checkMesh command. To visualize the mesh, you can use ParaView software by writing ParaFoam command. Here you see the gradient in the Y direction is applied. We can also check the boundaries. Turn on the front and the back only. And here you go. Let's see the upper wall, lower wall, inlet. Okay. Outlet. Okay, good. Let's have a look at the mesh data files. First one, points. blockMesh divides the domain into points and write them in this file here. If you open it, you find the points have two pieces of information, a location in the X, Y, and Z direction, and an index, which is known implicitly according to its order in the list. This index will be used later to define the faces. The second one is the faces file, which contains all the faces of the cells, and also have two pieces of information, the index of the points that represent each face. In this case, it's 4 points, and the index of each face, which is also known implicitly. So the faces here are divided into 3 types: boundary faces, internal faces in the neighbor file, and owner faces. This classification is needed by the solver to discretize the equations correctly using finite volume method. Most of the time, you will need to open the boundary file to check the name and the type of the boundaries, especially if you are converting a mesh from external tools. As the boundaries type and/or the name will be different. Let's now see the neighbor and owner files. And I think the data here is tricky to be understood, but it's okay, as most of the time you won't open these files at all. Let's explain some of these here. Index 0 here is saying the face number 0 is owned by cell number 0. Index 1 is saying face number 1 is owned by cell number 0. Let's pick a random one. Say this one here. It says face number 7 is owned by cell number 3. For the neighbor file, it will be face number 0 is the neighbor of cell number 1. So now we know that face number 0 is owned by cell 0 and neighbor of cell number 1. And the same here. The face number 1 is owned by cell 0 and neighbor of the cell number 120. And so on. Okay. Now we are done with the mesh. We move on to modify the other files to run the simulation and finish this lesson. First of all, we don't need these files that are related to the turbulence models, as our problem is laminar. We open the pressure file, check the dimensions, set the initial condition. I keep it 0. Boundary conditions. This name here should be the same as the one in the boundary file that we have seen before. So if you don't have a good memory like me, you can open them beside each other. Okay, the inlet is 0 gradient. I keep it. The outlet is atmospheric pressure, so I keep this one as well. The upper wall is symmetry, so we change this one. Lower wall is okay. Front and the back are empty, as we are solving for a 2D flow, so I will keep it. So now we modify the velocity file. You do the same procedures. The initial condition is 0. Init boundary is a fixed flow velocity. Let's keep it 1 to avoid high Reynolds number, as our problem is laminar, so you should calculate the Reynolds number before you run the analysis to make sure that the flow within range for the laminar flow. Because otherwise, maybe you will get problems in the simulation will run, but the analysis itself will not be correct. Okay, I keep the outlet, and the upper is symmetry plane. Lower is no slip, front and back empty. Okay. We are done with this and this. Now we open the transport properties. Here you see the transport model and the fluid viscosity. I keep them. Turbulence properties. I change the simulation type to be laminar. And I don't need this anymore. And that's it for the pre-processing. Now we move to the solver. We open controlDict. Do I have to change anything here? Maybe not. We just remove this function here. FV scheme. No modification. FV solution. No modification as well. So finally, we run the solver. No errors. I'm so happy. Okay, moving to the post-processing. Maybe we can plot two graphs, one for the velocity and the other for the pressure. Here you see the velocity over a line from the lower wall where the velocity is 0 to the center of the flow where the velocity is maximum. Let's see the pressure drop as well in the x direction. You now compare these plots to the analytical solution to validate your simulation results. I think I will stop here. So thanks and see you.